This is the video for the Chemquest number 42. On the first page, molarity, we know it as concentration or moles per 1 liter. The change, delta is change in, and the parentheses is molarity or concentration. The units would be molarity per second. And for number 4 and number 5, the change in molarity would always be m final minus m initial, and that would be based off the time. So the time that is furthest OA is the one that's the final, and the molarity that's corresponding to it. For number 4, this number would be negative because we're talking about the reactants. So if we were to react, for example, Alka-Seltzer plus water, and we got some oxygen gas, we're talking about the Alka-Seltzer. And if the amount of Alka-Seltzer at the final stage, after everything popped, was less than what you started with, which makes sense because it reacted. So if the final is the bigger, or if the final is the smaller number, in this case, this equation would yield a negative number. If this is smaller than the initial amount. And if that's the case for number 5, when it's talking about the products, we could think of it as the oxygen gas. In the beginning, or the M initial, it's a smaller amount, and in the final, it's a bigger amount. So if the final is a bigger amount than the initial, then in that case, this would be a positive number. For number 6, when writing the equation for the formation of a product, the negative sign in that original equation is not necessary. And that's the case because when we were talking about the product, we found that the change in molarity would be a positive number. So that negative number in the equation for the formation of the reactant, which we saw on the first page, is there just to cancel out the fact that we would have a negative number for the reactant itself. For number 7, we're just calculating the change between those 2 seconds. And for N2O5, which is the reactant, that change is a negative number, meaning that we're losing it. And for NO2 and O2, it's a positive number, meaning that we're gaining it. So in number 8, when it asks, based off the answers for question 7, do you see a relationship between the coefficients of the equation itself, which are 2, 4, and an imaginary 1 right there, and the number of moles used up? And we should see that the change, or the amount of change, has a correlation related there. We should be able to see that, for example, O2, the change being 0.0045, 4 times that gives you the change of NO2, and in the coefficients, as you can see, we have a 4:1 ratio between these things. Now, in terms of NO2 to the amount for N2O5, it's twice as much, disregarding the negative and the positive signs, because that just tells us whether we gained it or lost it. So what we have here is a 2:4 ratio between these two, and that just follows through with the equation with everything that we're comparing. And based off of this, we should be able to fill in the missing blanks above. In order to fill those 2 missing blanks, what we have to remember is that we're looking for the change in, not just the moles. So the ratio is the change between this and this. So the change here is actually 0.0036. Now if the change between O2 with those 2 seconds, or 2 bar rows, is 0.0036, then there has to be an equal factor in terms of the change of NO2 and the change of N2O5. So the factor here is 4 times. So NO2 is 4 times as much as O2, so it would be 4 times 0.0036, and that would give you the change. So now you have to remember that NO2 is a product, meaning that it is going up. So this would be, whatever this number is, you would add it to this number, and that should get you that final number. Now in the case of the reactants, you would calculate it again, and in this case it's 2 times based off the equation, and whatever this number is, it would be 0.4104 minus this number, because in the products we're gaining, and in the reactants we're losing. In order to calculate number 10 for A, the rate of disappearance, what we're doing, we could do it a couple of ways. We could calculate the molarity of each one of those bracket numbers that we had on the screen in the table and then do the change, or you could do the change in terms of moles and then figure out the molarity. So I did it based off the change in moles, and what we found was 0.0126 moles were lost, which is a negative amount, meaning lost. There are 3 liters. We know that from the experiment itself. You move that to 1 liter so that you can find the molarity, and we find that the molarity is 0.0042. So in order to find the rate of disappearance, it's just the molarity per seconds. So the time, or the change in seconds, is 600. So we have 0.0042 molarity divided by 600 seconds, which should give us 7 times 10 to the negative 6 molarity per second. And this is something that we are losing, and that is made evident to us by the fact that we call it rate of disappearance. And if you remember, if you had used a negative sign for the amount of change in terms of the moles, or in terms of the molarity, that's not a problem, because in the original equation there was a negative sign right here. So it would have canceled itself out. However, based off of the fact that I know it's lost, and based off the fact that it is rate of disappearance, I didn't want to make that, it's already made clear. For letters B and C, once again we find the change in moles. For letter B, it was 0.0252 moles that were changed in NO2. And we put that over 3 liters to find the molarity. And then we put that molarity over the same amount of time, 600 seconds, and we get that answer. And the same for C, and we should have got a change in moles of 0.0063, and then you figure out what the molarity is per 1 liter, and you put that over 600 seconds as well. For number 11, we should find that the same ratio exists between the rates of disappearance and appearance to and compared to the coefficients in the balanced chemical equation. For number 12, A, B, and C, you're doing it the same way you did number 10, A, B, and C. It's just a different number for the amount of moles lost, and therefore the number itself is going to be different. And number 13 is trying to wrap it up. As the reaction proceeds, are the rates constant? The rates we found for 12, A, B, and C are different from the rates that we found for 10, A, B, and C. And if you can look, it actually looks like all the rates are getting slower. And that makes sense, because based off of the activities that we did, if you have reactions proceeding based off of the collisions that are taking place, if you have many of the products are getting in the way, so you don't have as many of the reactions taking place. It reaches a certain point where it becomes equal. So the reaction doesn't speed up linearly, it actually slows down, and it doesn't slow down linearly either. It sort of has a pickup in the beginning of the reaction, and then it slowly peters off depending on the amount.